There's a monster at the center of our galaxy, a cosmic predator so massive it weighs 4 million times more than our sun. It's invisible, silent, devouring everything that comes too close, and we're orbiting it right now, 26,000 light-years away, trapped in its gravitational grip along with hundreds of billions of stars. This is Sagittarius, a star, the supermassive black hole eating the heart of the Milky Way. If understanding the beast that holds our galaxy together sounds worthwhile, a quick subscribe would mean the world to me, and drop a comment letting me know where you're watching from. Let's explore the void at the center of everything. When you look up at the night sky toward the constellation Sagittarius, you're looking toward the center of our galaxy. You can't see much. Dust clouds block visible light. The galactic center is hidden behind veils of gas and debris. But if you could see through that dust, if you had X-ray vision or could see radio waves, you'd witness something extraordinary. A dense cluster of millions of stars packed into a region smaller than our solar system. And at the very center of that cluster, nothing. A point of absolute darkness. An object so dense that light itself cannot escape. Sagittarius, a star. We call it Sg, a star, for short. Pronounced Sagittarius, a star. The star symbol isn't actually a star. It's an asterisk, a designation that stuck from early radio astronomy observations. Sagittarius A star is a supermassive black hole. But what does that actually mean? Let's start with black holes in general, because they're among the strangest objects in the universe. A black hole forms when matter becomes so dense that its gravity overwhelms everything else. Picture the sun. It's massive. Its gravity holds Earth in orbit from 93 million miles away. But the sun is also large, 860,000 miles in diameter. All that mass is spread out over a huge volume. Now imagine crushing the sun down. Smaller and smaller. Same mass, but less volume. The surface gravity increases. If you crushed the sun to the size of Earth, gravity at the surface would be intense. Objects would fall faster, light would bend, but you could still escape if you went fast enough. Keep crushing, down to the size of a city, a mountain, a house. Eventually, you'll reach a critical point, a size so small that the escape velocity, the speed needed to break free of gravity, exceeds the speed of light. And since nothing can travel faster than light, nothing can escape. You've created a black hole. The boundary where escape becomes impossible is called the event horizon. Cross that boundary and you're gone forever. You can't come back. You can't send signals out. You've fallen beyond the edge of the universe as far as outside observers are concerned. Inside the event horizon, all paths lead inward, toward the singularity. The singularity is the center of the black hole where all the mass is concentrated. We think it's a point of infinite density, though quantum mechanics suggests the reality might be more complicated. We don't really know what happens at the singularity. Our physics breaks down. General relativity, which describes gravity and space-time, gives us infinities. Nonsense answers. Quantum mechanics, which describes the very small, doesn't play well with gravity. We need a theory of quantum gravity to understand singularities. We don't have that theory yet, so the center of a black hole remains a mystery. But we understand event horizons pretty well, and for Sagittarius A star, the event horizon is enormous. Not because it's physically large compared to stellar black holes. Actually, Sagittarius A star's event horizon is only about 12 million miles in diameter. That sounds big, but it's tiny compared to the orbits of planets. It's less than the distance from the Sun to Mercury. For an object containing 4 million solar masses, that's incredibly compact. The density is mind-boggling. 4 million times the mass of the Sun, compressed into a region smaller than Mercury's orbit. To put this in perspective, if you could somehow gather all the mass of Sagittarius A star and spread it evenly across the volume inside its event horizon, it would be less dense than water. That's how much empty space there is even in a black hole. The mass is all that the singularity. The event horizon is just the point of no return. The boundary in space, not a physical surface. Understanding the scale of Sagittarius A star requires comparisons. 4 million solar masses. Let's break that down. The Sun is massive by human standards. It contains 99.86% of all the mass in our solar system. Everything else, all the planets, moons, asteroids, comets, dust, everything combined is less than 0.15%. The Sun dominates, and Sagittarius A star is 4 million times more massive than that. If you could somehow place Sagittarius A star in our solar system, its gravitational influence would be catastrophic. Every planet would be torn from its orbit. The entire solar system would spiral inward and be consumed within years or decades, depending on the initial positions. Earth wouldn't stand a chance. We'd fall into the event horizon and vanish. But Sagittarius A star is not in our solar system. It's 26,000 light-years away. That's the distance light travels in 26,000 years. Light moves at 186,000 miles per second. In 1 year, it covers about 6 trillion miles. Multiply that by 26,000 and you get the distance to the galactic center. It's a number so large it loses meaning, about 153 quintillion miles. You can't visualize it, you can't comprehend it, it's just far, very far. And that's good. That distance protects us. At 26,000 light-years, Sagittarius A star's gravity is just one force among many. The Sun holds us. The galaxy holds the Sun. Sagittarius A star contributes to the overall gravitational field of the galaxy, but doesn't directly threaten us. We orbit the galactic center at about 500,000 miles per hour. At that speed, it takes us about 230 million years to complete one orbit. The Sun has orbited the galaxy roughly 20 times since it formed 4.6 billion years ago. Earth has been around this cosmic merry-go-round 20 times. And Sagittarius A star has been at the center the entire time, quietly pulling everything into its dance. How did we discover Sagittarius A star? We couldn't see it directly. Black holes don't emit light. They're black. The event horizon is a one-way surface. Light that crosses it never comes back out. So you can't see a black hole by looking for light from it. You have to look for its effects on nearby matter. And that's what astronomers did. Starting in the 1990s, they began observing stars near the galactic center using infrared telescopes. Infrared light penetrates dust better than visible light. It allowed them to see through the obscuring clouds and watch stars in the galactic center region. What they found was astonishing. Stars moving incredibly fast, looping around a central point, orbiting something massive, something invisible. One star in particular, called S2, became famous. S2 is a bright blue star about 15 times more massive than the Sun. It orbits Sagittarius A star in a highly elliptical orbit with a period of about 16 years. At its closest approach, S2 comes within about 11 billion miles of Sagittarius A star. That's roughly the distance from the Sun to Neptune. But remember, this isn't a star S2 is orbiting. It's a black hole, an object with no physical surface, just an event horizon. S2 whips around this point at speeds up to 5,000 miles per second. That's almost 2% the speed of light. Astronomers tracked S2's position night after night, year after year. They measured its orbit with incredible precision, and from that orbit, using Newton's laws and Einstein's relativity, they calculated the mass of the object it was orbiting. 4 million solar masses, concentrated in a region smaller than the orbit itself. The only thing that could be is a supermassive black hole. This was confirmed by observing other stars too. There are dozens of stars in tight orbits around Sagittarius A star. Each one provides an independent measurement of the central mass. They all agree. 4 million solar masses, all concentrated at a single point, Sagittarius A star. The discovery earned the lead scientists, Reinhard Genzel and Andrea Ghez, a share of the 2020 Nobel Prize in Physics. They spent decades patiently observing, mapping orbits, refining measurements, building an ironclad case that yes, there is a supermassive black hole at the center of our galaxy, and we can measure it. We can study it. We can understand it even though we can't see it directly. But why does Sagittarius A star exist? Why do supermassive black holes exist at all? This is one of the biggest questions in astrophysics. We understand how stellar mass black holes form. When a massive star, at least 20 or 30 times the mass of the Sun, runs out of fuel, its core collapses. The collapse is so violent and rapid that it triggers a supernova. The outer layers of the star explode. The core continues collapsing into a black hole. This process creates black holes with masses between about 5 and 100 solar masses. We've observed many of these. They're relatively common, stellar remnants scattered throughout galaxies. But supermassive black holes are different. They're not just bigger stellar black holes. They're millions or billions of times more massive. Sagittarius A star at 4 million solar masses is actually on the smaller end for supermassive black holes. Some galaxies have black holes billions of times the Sun's mass. You can't create something that massive from a single star collapse. So, how did they form? We don't know for sure. There are theories. One idea is that supermassive black holes formed in the early universe from the direct collapse of massive gas clouds. Instead of fragmenting into stars, these clouds collapsed as a whole into black holes. Then, over billions of years, they grew by accreting matter and merging with other black holes. Another theory is that they started as stellar mass black holes that grew extraordinarily fast by consuming huge amounts of matter in the dense early universe. Or perhaps they formed from clusters of stars that collapsed together. Whatever the formation mechanism, we know that supermassive black holes are common. Almost every large galaxy has one at its center. This can't be a coincidence. There must be a connection between galaxies and their central black holes. In fact, observations show that the mass of a galaxy's central black hole correlates with properties of the galaxy itself, specifically with the mass of the galactic bulge, the central concentration of stars. Bigger bulge, bigger black hole. This suggests that galaxies and their supermassive black holes grow together. They co-evolve. The black hole influences the galaxy through its gravity and the energy it releases when feeding. The galaxy influences the black hole by funneling matter toward it. It's a symbiotic relationship. Neither can be understood in isolation. SGR A star doesn't feed much these days. It's relatively quiet, a dormant monster. We can tell because it's not very bright in X-rays or radio waves. When a black hole actively feeds, when it's pulling in large amounts of matter, that matter heats up to millions of degrees as it spirals inward. It emits intense radiation across the electromagnetic spectrum, X-rays, radio waves, gamma rays. This makes the black hole surroundings incredibly luminous. We call these active galactic nuclei, or AGN. Some are so bright they outshine their entire host galaxy. Quasars are the most extreme examples. Supermassive black holes feeding so voraciously that they're visible across billions of light years. SGR A star is not like that. It's dim, quiet, barely feeding. Observations suggest it accretes mass at a very low rate, maybe the equivalent of an Earth mass per year or even less. That's nothing compared to its total mass. At that rate, it would take trillions of years to double in size. So SGR A star is essentially starving. It grew rapidly in the past when the galaxy was forming and there was plenty of gas to consume. Now the galactic center has been mostly cleared out. The black hole sits in a relative desert. Occasionally something wanders too close. A gas cloud, a star. It gets shredded and consumed. But these events are rare. Most of the time, SGR A star just sits there, warping space-time, holding the galaxy together with its gravity, but not doing much else. That said, there is an accretion disk around SGR A star, matter that's orbiting the black hole, spiraling inward. This disk glows faintly. It's thin, sparse. Not the thick, luminous disk you'd see around an actively feeding black hole, but it's there, and it's visible in radio wavelengths and X-rays. Astronomers study this disk to understand how matter behaves in the extreme gravity near a black hole. The disk is turbulent. Magnetic fields twist through it. Gas heats and cools. Occasionally there are flares. sudden brightenings that last hours or days. These flares might be caused by clumps of matter falling into the black hole, or magnetic reconnection events similar to solar flares but on a much larger scale. We're still learning. Each observation adds a piece to the puzzle. In 2022, we got our most detailed view yet of Sagittarius A star. Not of the black hole itself, you can't see that, but of the environment around it. The Event Horizon Telescope, a global network of radio telescopes working together as a single Earth-sized instrument, captured an image of the emission near Sagittarius A star's event horizon. You might remember the 2019 image of the black hole at the center of M87, another galaxy. That was the first direct image of a black hole shadow. The Sagittarius A star image, released in May 2022, was the second, and it was harder to achieve. M87's black hole is over 1,000 times more massive than Sagittarius A star. That means its environment changes more slowly. You can stare at it for hours and it looks roughly the same. But Sagittarius A star is smaller. Its environment churns and changes on timescales of minutes. Trying to image it is like trying to photograph a toddler. It won't hold still. The researchers had to use clever techniques to process the data, essentially averaging over many observations to get a clear picture. The image shows a ring of bright emission surrounding a dark central region. The dark region is the black hole's shadow. It's not the event horizon itself. It's a larger region where light has been bent and captured by the black hole's gravity. The bright ring is light from the accretion disk, bent by the extreme space-time curvature near the event horizon. This bending amplifies and distorts the light, creating the ring structure. The image confirms predictions from Einstein's general relativity. The size and shape of the shadow match what theory predicts for a 4 million solar mass black hole. It's visual proof. We're looking at the edge of a black hole, the boundary between our universe and whatever lies beyond. The gravitational effects near Sagittarius A star are extreme. Space-time is severely warped. To understand what this means, you need to think about gravity differently. In everyday experience, gravity is a force. Things fall down. Earth pulls on you. You pull on Earth. This is Newton's picture, and it works well for most purposes. But it's incomplete. Einstein showed that gravity is not a force. It's the curvature of space-time. Mass and energy warp the fabric of space and time. Objects moving through this warped space-time follow curved paths. We perceive this as gravity. Near Sagittarius, a star, the warping is so severe that space-time itself is twisted into bizarre shapes. Light doesn't travel in straight lines. It follows the curves, circles and spirals. Time runs at different rates depending on how deep you are in the gravitational field. Clocks near the event horizon tick slower than clocks far away. This is time dilation, a real measurable effect. If you could somehow survive near Sagittarius A star, physics would get weird fast. Tidal forces would be your first concern. Tidal forces arise because gravity gets stronger the closer you are to the source. If you're falling feet first toward a black hole, Your feet are closer than your head. They experience stronger gravity. This difference in gravitational pull stretches you. Near a stellar mass black hole, tidal forces would rip you apart long before you reached the event horizon. Your body would be stretched like taffy, a process gruesomely called spaghettification. But Sagittarius A star is so massive, and its event horizon so large, that tidal forces at the event horizon are actually relatively gentle. You could cross the event horizon intact. You'd be doomed. You can't escape, but you'd still be in one piece for a while. Deeper inside, closer to the singularity, tidal forces increase without limit. Eventually, you'd be shredded down to atoms, then subatomic particles, then who knows? The singularity is the end of the line. Physics, as we know it, stops. Another weird effect is frame dragging. Sagittarius A star is spinning. We know this from observations of the accretion disk and the behavior of matter near the event horizon. When a massive object spins, it drags space-time around with it, like a spoon stirring honey. Near a spinning black hole, space-time is twisted into a spiral. If you tried to hover near the event horizon, you'd find yourself being pulled along with the rotation. You'd have to fire rockets constantly to stay in place, and close enough to the event horizon, in a region called the ergosphere, it becomes impossible to stay still. You're forced to rotate with the black hole. This isn't because of friction or magnetic fields. It's space-time itself rotating. The geometry of the universe is twisted. It's a consequence of general relativity, and it's been confirmed by observations of black holes and neutron stars. The universe is far stranger than our intuition suggests. Let's talk more about the stars that orbit Sagittarius A star, because they're fascinating laboratories for testing physics. The innermost cluster of stars, called the S stars, have orbital periods ranging from a few years to decades. S2, which we mentioned, has a 16-year orbit. But there are stars even closer. S62 has an orbital period of just 9.9 years and passes within about 900 million miles of the event horizon. That's closer than Earth is to the Sun. Imagine a star, a massive ball of nuclear fire, whipping past a black hole at relativistic speeds. The precision measurements of these orbits have revealed effects predicted by Einstein's general relativity that can't be explained by Newton's gravity alone. One such effect is gravitational redshift. Light escaping from a deep gravitational well loses energy. Its wavelength stretches, shifting toward the red end of the spectrum. When S2 makes its closest approach to Sagittarius A star, it's deep in the black hole's gravitational field. Light emitted from S2 at that point is gravitationally redshifted when it reaches us. Astronomers measured this redshift and found it matched Einstein's predictions perfectly. This is a direct test of general relativity in a regime of strong gravity. Newton's theory would predict no such effect. Einstein's theory does, and observation confirms Einstein. It's one of the most stringent tests of general relativity ever performed. Another effect is orbital precession. In Newton's gravity, a planet or star in an elliptical orbit returns to exactly the same point in space with each orbit. The ellipse is fixed. But in Einstein's gravity, the ellipse itself rotates. The point of closest approach shifts slightly with each orbit. This precession is tiny for planets in our solar system. Mercury's orbit precesses by about 43 arc-seconds per century due to relativistic effects. That's about 1/100th of a degree per century. Tiny, but measurable. And it was one of the first confirmations of general relativity back in the early 1900s. For S2 orbiting Sagittarius A star, the precession is much larger, about 12 arc-minutes per orbit. That's about 1/5 of a degree, much easier to measure. And, again, observations match Einstein's predictions precisely. S2's orbit is a cosmic laboratory where we can watch general relativity in action. There are other stars even closer to Sagittarius A star that we're discovering. As telescopes improve, we find fainter, faster stars in tighter orbits. Some might have orbital periods of just a few years. These stars are on the edge. One small perturbation, one close encounter with another star, and they could be flung inward. They'd cross the event horizon and vanish. Or they'd be ejected at high speed, escaping the galactic center entirely. It's a violent, chaotic environment, and it's a miracle these stars survive at all. The tidal forces, the gravitational interactions, the radiation, everything conspires to destroy them, but they persist, dancing around the abyss. We also need to understand what Sagittarius A star is actually eating right now. The accretion rate is low, but not zero. Where is the material coming from? Some of it is stellar winds. Stars near the galactic center are massive and hot. They lose mass through powerful stellar winds. Material streaming off their surfaces at thousands of miles per second. This material diffuses through space. Some of it gets captured by Sagittarius A star's gravity. It spirals inward, joins the accretion disk, eventually crosses the event horizon. The star has unwittingly fed the monster. But there are more dramatic feeding events too. Occasionally, a gas cloud wanders too close. In 2011, astronomers discovered a cloud called G2 heading toward Sagittarius A star. It was predicted to make its closest approach in 2014. There was excitement and speculation. Would the cloud be torn apart? Would it produce a burst of activity as it was consumed? Would we see a dramatic flare? Telescopes around the world prepared to observe. 2014 came. G2 made its closest approach, and nothing dramatic happened. The cloud survived. It was stretched and distorted, but not destroyed. This told us something about the cloud's nature. It might not have been just a gas cloud. It might have had a star embedded in it. The star's gravity could have held the gas together, preventing total disruption. Or the cloud was denser than expected. Either way, it was a disappointing non-event for those hoping for fireworks. But it was scientifically valuable. We learned about the conditions near Sagittarius A star and the resilience of objects in that environment. There's also the question of what happens to stars that get too close. Not close enough to cross the event horizon, but close enough to be tidally disrupted. A tidal disruption event happens when a star passes near a black hole and the tidal forces tear it apart. The star is stretched into a long stream of gas. Some of this gas has enough energy to escape. It's flung away at high speed, but about half the gas doesn't have enough energy. It falls back toward the black hole. It forms an accretion disk, and as it spirals inward, it heats up and emits intense radiation. For a brief period, weeks to months, the black hole becomes thousands of times brighter. Then, the extra material is consumed. The black hole fades back to its normal dim state. We've observed tidal disruption events around other supermassive black holes in distant galaxies. Sudden bright flares that match the expected signatures. But we haven't seen one around Sagittarius A star. Not yet. It's probably just a matter of time. Estimates suggest Sagittarius A star disrupts a star every 10,000 to 100,000 years. That means we might not see one in our lifetimes. But we might. And if it happens, it will be spectacular. Every telescope on Earth and in space will turn toward the galactic center. We'll watch in real time as a star dies, torn apart by gravity, feeding a black hole. It will be a cosmic feast, a rare opportunity to study the physics of accretion in detail. The radiation environment around Sagittarius A star is also worth discussing. Even though the black hole is relatively quiet, the galactic center is not a calm place. There are many massive stars. Each one produces ultraviolet light and stellar winds. There are supernova remnants, the expanding shells of gas from exploded stars. These remnants glow in X-rays and radio waves. There are pulsars, rapidly spinning neutron stars emitting beams of radiation. There are cosmic rays, high-energy particles zipping through space at nearly the speed of light. All of this creates a background of radiation that's far more intense than what we experience in our quiet corner of the galaxy out in the suburbs. If you could somehow visit the galactic center, you'd need serious radiation shielding. The levels would be lethal to unprotected humans in short order. And we haven't even mentioned the jets yet. Many actively feeding black holes produce jets. Powerful streams of matter and energy shooting out from the poles of the black hole at relativistic speeds. These jets can extend for millions of light years. They're visible in radio waves and X-rays. They're one of the most energetic phenomena in the universe. But Sagittarius A star doesn't have strong jets. Not currently. This is strange because most supermassive black holes that we can study in detail have jets when they're feeding. The absence of strong jets from Sagittarius A star tells us something about its current state. It's feeding so slowly that it can't generate powerful jets. Or perhaps the geometry of the accretion disk doesn't favor jet formation. There might be weak jets, small-scale outflows of material, but nothing like the dramatic jets we see in other galaxies. However, there's evidence that Sagittarius A star had powerful jets in the past. Observations of the region around the galactic center show structures called Fermi bubbles. These are giant lobes of hot gas extending above and below the galactic plane. They're huge, about 25,000 light-years tall each. They emit gamma rays, the highest energy form of light. The exact origin of these bubbles is debated, but one plausible explanation is that they were created by jets from Sagittarius A star a few million years ago. Back when the black hole was feeding more actively, it produced powerful jets. These jets plowed into the gas above and below the galaxy, creating shock waves. The shocked gas expanded into the enormous bubbles we see today. If this interpretation is correct, it means SGR A star was much more active in the recent past. Geologically recent. A few million years is nothing in cosmic terms. It raises questions. What caused the feeding episode? Did SGR A star consume a giant gas cloud? Did another galaxy pass through ours, funneling gas toward the center? We don't know, but it's a reminder that black holes can be dormant for long periods and then suddenly become active. Let me also clarify something about the term eating. When we say SGR A star is eating the center of the galaxy, we don't mean it's consuming the entire galaxy. It's not gobbling up stars hand over fist. The vast majority of stars in the galaxy are in no danger of falling into the black hole. They're in stable orbits. They'll circle the galactic center for billions of years without getting any closer. The eating refers to the gradual accretion of gas and the occasional consumption of objects that wander too close. Over the lifetime of the galaxy, SGR A star has probably consumed thousands of stars and vast amounts of gas. But the galaxy contains hundreds of billions of stars. Even if SGR A star consumed 1 million stars, it's a tiny fraction. The galaxy is not being devoured. It's more like the black hole is nibbling at the edges, taking small bites when opportunity presents. There's also a common misconception that black holes are cosmic vacuum cleaners, that they suck in everything around them. This isn't true. Black holes are gravitational objects like any other. They don't suck, they pull. Just like the sun pulls on Earth, just like Earth pulls on the moon. If you replace the sun with a black hole of the same mass, Earth's orbit wouldn't change. We'd keep orbiting at the same distance with the same period. We'd freeze because the black hole doesn't emit light, but we wouldn't get sucked in. The gravitational influence would be identical. Black holes are only dangerous if you get too close. Within a few event horizon radii, tidal forces become extreme. Within one event horizon radius, escape is impossible. But farther away, they're just massive objects with gravity, not magical vacuum cleaners. This is important for understanding SGR A star's role in the galaxy. It's not actively destroying the galaxy, it's holding it together. The mass of SGR A star contributes to the overall gravitational potential of the galactic center. This potential helps stabilize the orbits of stars. Without the central mass concentration, the galaxy's structure would be different. Stars would orbit differently. The spiral arms might not form the way they do. Galactic evolution is a complex interplay between dark matter, normal matter, star formation, and supermassive black holes. Remove any one component and the galaxy changes in fundamental ways. SGR A star is a key player in this story, not a destroyer, a stabilizer, a central anchor around which the galaxy rotates. Now, let's think about the DGAO information paradox, because it's one of the deepest mysteries in physics, and black holes are at the center of it. When something falls into a black hole, it seems like information is lost. The object had properties: mass, charge, spin, the arrangement of its atoms, its quantum state. All of that crosses the event horizon and vanishes. From the outside, all we can measure is the black hole's mass, charge, and spin. Nothing else. John Wheeler famously said black holes have no hair, meaning they have no other distinguishing features. Everything else is hidden behind the event horizon. But quantum mechanics says information can't be destroyed. It can be scrambled, transformed, but not lost. This creates a paradox. General relativity says information is lost inside black holes. Quantum mechanics says it can't be. Both theories can't be right. Stephen Hawking worked on this problem for decades. In the 1970s, he discovered that black holes aren't completely black. They emit radiation due to quantum effects near the event horizon. This Hawking radiation carries away energy. Over enormous timescales, a black hole can evaporate completely. For Sagittarius A star, the evaporation time is unimaginably long, about 10 to the 100 years. That's a 1 followed by 100 zeros, far, far longer than the current age of the universe. The universe is only about 14 billion years old. That's 10 to the 10 years. Sagittarius A star will outlast the stars. It will outlast galaxies. It will sit in the cold, dark, empty universe, emitting faint Hawking radiation for eons beyond comprehension. And eventually, it will evaporate into nothing. All the information it consumed over its lifetime, what happens to it? Does it come out in the Hawking radiation, or is it truly lost? This is the information paradox, and we still don't have a definitive answer. Recent theoretical work suggests information is preserved. It's encoded in the Hawking radiation in subtle ways. But proving this requires a theory of quantum gravity, which we don't have. So the paradox remains. For Sagittarius A star specifically, the information paradox is academic. The evaporation timescale is so long that we'll never observe it. But the paradox matters for our understanding of fundamental physics. It tells us our theories are incomplete. General relativity is incomplete. Quantum mechanics is incomplete. We need a deeper theory, a theory that unifies them. String theory is one candidate. Loop quantum gravity is another. There are others, but none have been confirmed. None make testable predictions we can check with current technology. So we remain in the dark. We have two brilliant theories that work perfectly in their domains, but they contradict each other when you push them to extremes. Black holes are one extreme. The Big Bang is another. Until we solve this, our understanding of the universe is fundamentally limited. Let's dig deeper into what the first image of Sagittarius A star tells us and why it was so difficult to capture. The Event Horizon Telescope isn't a single telescope. It's a network of radio telescopes scattered around the globe, from Hawaii to Chile to Antarctica to Europe. Each telescope observes the target simultaneously. The data from all telescopes is combined using a technique called very long baseline interferometry. Essentially, you're creating a telescope the size of Earth. The larger the telescope, the better the resolution, the finer the details you can see. But coordinating observations across the globe is challenging. All the telescopes need to point at the same target at the same time. They need perfect synchronization. Atomic clocks at each site keep time to within billionths of a second. The data is recorded on hard drives. Then the hard drives are physically shipped to correlation centers where supercomputers combine the data. For M87's black hole, the process was straightforward. Well, as straightforward as this kind of thing can be. The black hole is massive, 6.5 billion solar masses. Its environment is stable over the observation period. You can observe for many hours and the image doesn't change much. But Sagittarius A star is different. 4 million solar masses, much smaller. Its accretion disk churns and changes on timescales of minutes. In the time it takes to do a complete observation, the structure has evolved. It's like trying to photograph a squirming child. You get blur, distortion. The image is smeared. So the researchers had to develop new analysis techniques. They took many snapshots. Each one captured the structure at a particular moment. Then they used statistical methods to extract the average structure. What features are consistent across all the snapshots? What's variable? The ring structure is consistent. The dark central shadow is consistent. The brightness varies, but the overall geometry is stable. This average structure is what you see in the published image. The image also confirms that Sagittarius A star is spinning. The brightness of the ring is not uniform. It's brighter on one side. This asymmetry is caused by relativistic beaming. Material in the accretion disk is moving at a significant fraction of light speed. On the side moving toward us, the light is blue shifted and brightened. On the side moving away, it's red shifted and dimmed. This creates the brightness asymmetry. By measuring this effect, researchers can infer the spin of the black hole. Sagittarius A star is spinning, but not at maximum rate. It's rotating at about 60% of the maximum spin allowed by physics. If it were spinning faster, the event horizon would be smaller. At maximum spin, a black hole's event horizon shrinks to about half the size it would be if it weren't spinning. So Sagittarius A star is rotating significantly, but not at the extreme. Why does spin matter? Because spinning black holes have different properties than non-spinning ones. A spinning black hole has an ergosphere, a region outside the event horizon where space-time is dragged around. In the ergosphere, you can extract energy from the black hole. A process called the Penrose process allows you to throw something into the ergosphere in just the right way, and it splits into two parts. One part falls into the black hole. The other escapes with more energy than the original object had. The extra energy comes from the black hole's rotation. You've stolen rotational energy. Do this enough and you can slow the black hole's spin. This process might power some of the most energetic phenomena in the universe. Quasars, jets, gamma-ray bursts, all potentially tapping into the rotational energy of supermassive black holes. Sagittarius A star doesn't produce these phenomena now because it's not feeding enough. But if it ever becomes active, its spin could be a source of tremendous energy. The comparison between Sagittarius A star and other supermassive black holes is illuminating. M87's black hole is over 1,000 times more massive. It's in an elliptical galaxy a completely different environment. Elliptical galaxies are older, more evolved. They've consumed most of their gas. Star formation has mostly stopped. They're red and dead, as astronomers say. But M87's black hole is still active. It's producing a powerful jet that extends for thousands of light years. Why? Probably because M87 is in a cluster of galaxies. It's surrounded by other galaxies. Occasionally, gas from neighboring galaxies or from the intergalactic medium falls into M87. This provides fuel for the black hole. Sagittarius A star doesn't have this advantage. The Milky Way is in a relatively isolated region. Our nearest large neighbor, Andromeda, is 2.5 million light years away. We're not getting fresh gas from outside, so Sagittarius A star starves. But in a few billion years, this will change. The Milky Way and Andromeda are on a collision course. Gravity is pulling them together. In about 4 billion years, they'll collide. Now, when galaxies collide, stars don't actually hit each other. The distances between stars are vast. It's like throwing two swarms of bees at each other. The bees might pass through without colliding, but the gas clouds collide. They shock and compress. This triggers bursts of star formation, and it funnels gas toward the centers of both galaxies. Sagittarius A star will wake up. It will feast on the inflowing gas. It might become a quasar, brilliant, energetic, visible across the universe, and the Milky Way and Andromeda's supermassive black holes will spiral toward each other. Over hundreds of millions of years, they'll merge, creating a single supermassive black hole, perhaps 5 or 6 million solar masses. This merger will produce gravitational waves, ripples in space-time that spread out at the speed of light. We won't be around to see it. Humanity will be long gone. The sun will have swelled into a red giant and consumed Earth. But the event will happen. The monster at the center of our galaxy will merge with Andromeda's monster, creating an even larger monster at the center of the new merged galaxy. Let's talk about the extreme environment near Sagittarius A star in more detail. The galactic center is dense, really dense. In our region of the galaxy, the nearest star to the Sun is Proxima Centauri, about 4 light years away. In the galactic center, stars are separated by light weeks or light days, sometimes light hours. They're packed together so tightly that close encounters are common. Stars pass near each other. Gravitational interactions fling stars around. Some are ejected at high speed. These are called hypervelocity stars. They're traveling so fast that they can escape the galaxy entirely, hundreds of miles per second. Fast enough to leave the Milky Way and drift into intergalactic space. We've found several hypervelocity stars in our surveys. Each one is a refugee from the galactic center, ejected by gravitational slingshot interactions, probably involving Sagittarius A star. A star approaches the black hole. Another star is nearby. The complex three-body interaction accelerates one star to escape velocity while the other is captured or consumed. It's a violent process, and it happens regularly in the dense core of the galaxy. The density of stars also means stellar collisions are possible. In most of the galaxy, stellar collisions are extraordinarily rare, but in the galactic center, they might happen every few million years. When two stars collide, they can merge, forming a larger, hotter, more massive star. Or they can disrupt each other, tearing each other apart in a catastrophic explosion. Either way, it's dramatic, and it adds to the chaotic, violent nature of the galactic center. This is not a place where planetary systems can survive. Any planets orbiting stars in the galactic center would be stripped away by close encounters or sterilized by radiation. Life as we know it could not exist there. It's a hostile environment. Beautiful in its extremity but deadly. There's also a population of old stellar remnants near Sagittarius A star. White dwarfs, neutron stars, stellar mass black holes. These are the corpses of massive stars that died in supernovae. They're invisible or very faint, but they're there. Dense objects quietly orbiting the central black hole. Occasionally, one gets too close. It's captured into a tight orbit. If it's a white dwarf or neutron star and there's a companion star, matter from the companion can flow onto the compact object. This creates an X-ray binary, a bright X-ray source powered by accretion. Several X-ray binaries have been found near the galactic center. Each one is a compact object feeding on a companion star, emitting intense X-rays as matter spirals inward and heats to millions of degrees. These systems are laboratories for studying extreme physics, matter under conditions we can't replicate on Earth. Densities, temperatures, magnetic fields, all pushed to the limit. And if a stellar mass black hole falls into Sagittarius A star, what happens? The smaller black hole doesn't immediately merge with the larger one. It orbits inside Sagittarius A star's event horizon. Wait, can you orbit inside an event horizon? Actually, yes, but not for long. Inside the event horizon, all paths lead inward. But the inward fall isn't instantaneous. You can orbit for a while, spiraling down, emitting gravitational waves as you go. These gravitational waves carry away energy. The orbit shrinks faster and faster, until finally the two black holes merge. The event horizons touch and combine, forming a single larger event horizon, a single larger black hole. This merger produces a burst of gravitational waves, much weaker than the mergers we've detected with LIGO because the masses are smaller and the event is farther away, but in principle detectable by future gravitational wave observatories. Each merger tells us about the population of black holes in the galactic center. How many stellar mass black holes are there? How often do they fall into Sagittarius A star? These questions help us understand galactic evolution. One thing that's remarkable about Sagittarius A star is how stable it is. Despite being a roiling, turbulent environment, the black hole itself is eternal, or nearly so. It will exist for unimaginable timescales, long after the sun dies, long after the Milky Way merges with Andromeda, long after star formation stops and the universe goes dark. Black holes will be among the last objects to exist. In the far future, trillions of years from now, the universe will be cold and dark. All the stars will have burned out, planets will be frozen, Galaxies will be scattered by the expansion of space, but black holes will remain, slowly evaporating via Hawking radiation. Sagittarius A star will sit in the darkness, emitting faint radiation, gradually losing mass. After 10 to the 100 years, it will finally evaporate completely. A flash of radiation as the last bit of mass converts to energy, and then nothing. Empty space, that's the ultimate fate. Heat death, maximum entropy, no structures, no complexity, just photons spreading through an ever-expanding, ever-cooling void. It's a bleak picture, but it's also distant. Inconceivably distant. For now, for the next trillions of years, black holes and their remnants will persist, silent monuments to the stars and galaxies that once were. But let's return to the present, to the here and now. We're living in an era where we can study black holes directly, where we can image them, track their effects, test fundamental physics using them. This is extraordinary. A century ago, black holes were purely theoretical, solutions to Einstein's equations, mathematical curiosities. Most physicists doubted they existed in nature. Now we know they're common. Millions of stellar mass black holes in our galaxy alone, supermassive black holes in most galaxies. We've imaged 2 of them. We've detected gravitational waves from merging black holes. We've measured their masses and spins. Black holes have gone from fantasy to reality. And the technology continues to improve. Future telescopes will give us even sharper images. We'll watch material spiraling into Sagittarius A star in real time. We'll see relativistic effects in action, frame dragging, time dilation, gravitational lensing, all visible in the data. It's a golden age for black hole research, and there's still so much we don't know. How exactly do supermassive black holes form? What happens at the singularity? Is information truly preserved? Can we develop a theory of quantum gravity? These are some of the deepest questions in science, and black holes are the key to answering them. They're extreme environments where our theories are pushed to breaking point, where we can test ideas that would be impossible to test anywhere else. Every observation of Sagittarius A star adds to our knowledge. Every measurement refines our understanding. We're piecing together the story of the monster at the heart of our galaxy, and through it, learning about the nature of reality itself. Think about the journey that light takes from the galactic center to reach your eyes. 26,000 years of travel. The photons that enter your eye tonight when you look towards Sagittarius, those photons began their journey 26,000 years ago, before human civilization, before agriculture, before cities, when humans were nomadic hunter-gatherers living in small groups, chasing game across ice age landscapes. Those photons have been traveling through space all this time, crossing vast distances, passing other stars, other gas clouds, arriving at Earth in the 21st century to be captured by your retina or by a telescope's detector. It's humbling. The light is ancient. It carries information about what the galactic center looked like in the distant past, not as it is now. As it was, we're seeing the past, always the past, and if there were observers 26,000 light years on the other side of the galactic center looking back toward us, they'd see our region of the galaxy as it was 26,000 years ago, long before recorded history. It's a strange consequence of light's finite speed. The universe is not a single moment. It's a collection of different moments depending on where you look and how far away it is. This also means that if Sagittarius A star suddenly became active tomorrow, if it started consuming a massive gas cloud and brightened dramatically, we wouldn't know for 26,000 years. The event would happen, the black hole would feast, radiation would stream out. But that radiation has to travel to reach us, 26,000 years at light speed. By the time we saw the burst of light, the event would be ancient history. The black hole might have settled back down, gone quiet again, but we'd be seeing the fireworks for the first time, and we'd have no way to know what's happening at the galactic center right now. This moment, the present moment. We're always looking into the past. The nearest star, Proxima Centauri, is 4 light years away. We see it as it was 4 years ago. The Sun is 8 light minutes away. We see it as it was 8 minutes ago. The farther you look, the further back in time you see. Distant galaxies, billions of light years away, we see them as they were billions of years ago, in the early universe, when the cosmos was young. Astronomy is time travel. We observe the past. We study history written in light. This brings us to a profound realization. Sagittarius A star has been there at the center of the galaxy for billions of years, before the sun formed, before Earth existed, before life began. The black hole was already ancient, massive, powerful, holding the galaxy together. It will be there long after we're gone, after the sun dies, after Earth is consumed, after the last human draws their last breath. The black hole will remain, indifferent to our existence. We're a fleeting moment in cosmic history, a brief spark of consciousness that arose, wondered at the universe, and will eventually fade. But the universe continues. The galaxies spin. The black holes persist. It's both humbling and inspiring. Humbling because we're so small, so temporary. Inspiring because despite our smallness, we can understand. We can look at a black hole 26,000 light years away and comprehend what it is. We can measure its mass, map its effects, image its shadow. We're tiny, but we're capable of understanding the vast. That's the miracle of consciousness, of intelligence, of science. We transcend our limitations through thought, through observation, through the slow, patient accumulation of knowledge across generations. Sagittarius A star is a reminder that the universe is full of wonders, objects and phenomena that challenge our imagination, that push the boundaries of what's possible, that reveal deep truths about the nature of reality. We live in an age where these wonders are accessible. We have telescopes, spacecraft, computers, theories. We can explore the cosmos from the comfort of Earth. We can see things our ancestors never imagined, and every discovery raises new questions. Every answer leads to deeper mysteries. That's the beauty of science. It's an endless frontier. There's always more to learn, more to discover, more to understand. Sagittarius A star is one chapter in this story, the monster at the center of our galaxy, but it's connected to everything else, to the formation of galaxies, to the nature of gravity, to the fate of the universe. Understanding it helps us understand ourselves, our place, our origins, our future. The stars that orbit closest to Sagittarius A star are more than just test particles for general relativity. They're survivors in the most extreme stellar environment in the galaxy. These S stars, as they're called, are young. Most are only a few million years old. This is puzzling. The tidal forces near a black hole should prevent star formation. Gas clouds should be torn apart before they can collapse into stars. So, how did these stars form so close to Sagittarius A star? One theory is that they formed farther out and then migrated inward. Gravitational interactions with other stars could have changed their orbits, bringing them closer to the black hole over time. Another theory is that they formed from a massive gas disk that existed around Sagittarius A star in the past. A disk so massive and dense that despite the tidal forces, portions of it could collapse into stars. We don't know which explanation is correct. Maybe both processes happened. Maybe there are multiple generations of stars with different origins. What we do know is that these stars are on borrowed time. Their orbits bring them perilously close to the event horizon. S62, for instance, passes within about 900 million miles. That's incredibly close in cosmic terms. If another star or massive object perturbed S62's orbit slightly, it could be pushed inward. It would cross the event horizon. It would vanish. The black hole would gain a tiny amount of mass. A rounding error in Sagittarius A star's 4 million solar mass budget. But the star would be gone, utterly destroyed, not exploded, not fragmented, simply removed from the universe. Every atom, every electron, every photon the star ever emitted, all of it would fall into the singularity. And from the outside, we'd see the star freeze at the event horizon. Time dilation would slow the star's clock to a stop from our perspective. The star would redshift into invisibility. It would fade from view as if it never existed. This brings up a peculiar aspect of black holes, the frozen star paradox. When something falls into a black hole, an outside observer never actually sees it cross the event horizon. As it approaches, time dilation becomes extreme. The object's clock slows. From our perspective, it takes forever to reach the event horizon. It gets closer and closer, but never quite crosses. Meanwhile, the infalling object is red-shifted. The light from it shifts to longer wavelengths: red, infrared, radio. Eventually, the wavelength becomes so long that the light is undetectable. The object fades from view. So, from the outside, objects don't fall into black holes. They freeze at the horizon and fade away. But from the infalling object's perspective, nothing special happens at the horizon. It crosses smoothly. Time passes normally for the infalling observer. They cross the event horizon and continue falling toward the singularity. Both perspectives are correct. It's just relativity. Different observers experience time differently. The radiation emitted by material near Sagittarius A star tells us a lot about conditions there. Most of the emission is in radio wavelengths and X-rays. Very little visible light. This is characteristic of hot, thin plasmas. The accretion disk around SGR A star is sparse, not much material. What's there is heated too, millions of degrees, by friction and magnetic fields. At these temperatures, atoms are fully ionized, electrons stripped away from nuclei. This plasma emits radiation through various processes. Synchrotron radiation from electrons spiraling around magnetic field lines. Bremsstrahlung, or breaking radiation from electrons scattering off ions. And thermal emission from the hot gas itself. By studying the spectrum, the distribution of radiation across different wavelengths, astronomers can infer the temperature, density, and magnetic field strength of the plasma. One surprising finding is that the plasma is magnetized. Magnetic fields thread through the accretion disk. These fields are generated by the motion of the electrically charged plasma. As the plasma spirals inward, it drags magnetic field lines with it. The fields twist and tangle. They store energy. Sometimes they reconnect, releasing that energy in bursts. This might explain the flares that Sagittarius A star occasionally produces. Sudden brightenings that last for hours. The flares are not well understood. They could be caused by magnetic reconnection, or by clumps of material falling into the black hole, or by hotspots in the accretion disk. Each flare is an opportunity to study the environment near the event horizon in detail. Telescopes around the world and in space coordinate to observe whenever a flare is detected, capturing data across multiple wavelengths simultaneously, building a picture of what's happening. Now, let's compare Sagittarius A star to the supermassive black holes in other galaxies. Most large galaxies have central black holes, but their activity levels vary wildly. Some are dormant like Sagittarius A star, others are incredibly active. Active galactic nuclei, or AGN, are among the most luminous objects in the universe. The central black hole is surrounded by a thick accretion disk. Material spirals inward at tremendous rates. Perhaps the equivalent of several solar masses per year. This material heats to tens of millions of degrees. It emits intense radiation across the spectrum. The core of the galaxy outshines all the stars combined. In extreme cases, called quasars, the AGN is so bright it can be seen across billions of light years. Quasars were more common in the early universe when galaxies were forming and there was more gas available to feed black holes. Today, they're rare. Most supermassive black holes have consumed their nearby gas and settled into dormancy. But some galaxies still have active black holes. M87, the galaxy whose black hole was first imaged by the Event Horizon Telescope, has an active nucleus. Its black hole is producing a powerful jet. This jet is a stream of plasma and energy shooting out from near the event horizon at nearly the speed of light. The jet extends for thousands of light years. It plows into the surrounding gas, creating shock waves and heating the material. The jet is powered by the rotational energy of the black hole and the magnetic fields in the accretion disk. It's one of the most energetic phenomena in the universe. Why does M87 have a jet while Sagittarius A star doesn't? The key is the accretion rate. M87's black hole is feeding much more actively. It has more material to work with, more fuel. This creates a thicker, more powerful accretion disk. The magnetic fields are stronger. The conditions are right for jet formation. SGR A star doesn't have enough material. Its accretion disk is too thin and weak to generate a powerful jet. But this could change. If a large gas cloud or another galaxy came close to the Milky Way, funneling gas toward the center, SGR A star could become active. It could develop an accretion disk like M87's. It could produce jets. It could become a quasar. Our galaxy would look completely different. The core would be brilliant, visible across the universe. Any planets near the galactic center would be sterilized by the radiation. The jets would plow through the galaxy, disrupting star formation, heating the gas. It would be a violent transformation, and it will happen. When the Milky Way and Andromeda collide in a few billion years, Sagittarius A star will wake up. It will feed on the gas stirred up by the collision. For a cosmologically brief period, perhaps a few million years, our galaxy will host an active galactic nucleus. Then the fuel will run out. The black hole will settle back into dormancy. But for that brief window, Sagittarius A star will blaze. The environment around Sagittarius A star is not just extreme in terms of gravity and radiation. It's also extreme in terms of stellar density and dynamics. In our region of the galaxy, the solar neighborhood, there's about 1 star per cubic light year on average. That's very sparse. Stars are separated by light years. Collisions are essentially impossible, but in the central parsec around Sagittarius A star, a region about 3 light years in radius, there are millions of stars. The density is about million times higher than in the solar neighborhood. Stars are separated by light days or light hours. They pass close to each other regularly. Every few thousand or tens of thousands of years, a close encounter occurs. 2 stars approach within a few AU, a few times the Earth-Sun distance. The gravitational interaction can change their orbits dramatically. 1 star might be flung inward toward the black hole. The other might be ejected at high speed. These hypervelocity stars are fascinating. We've detected several dozen of them in surveys of the galaxy. They're traveling at hundreds of kilometers per second relative to the galaxy, fast enough to escape the Milky Way's gravity. They're on ballistic trajectories that will take them into intergalactic space. In a few billion years, they'll be millions of light years away, drifting alone in the void between galaxies. How did they get their speed? The most likely explanation is that they were part of binary star systems that passed close to Sagittarius A star. The black hole's gravity disrupted the binary. 1 star was captured into a tight orbit or fell into the black hole. The other was accelerated to high speed by the gravitational slingshot effect. It shot away from the galactic center at breakneck speeds. We can trace the paths of these hypervelocity stars backward in time. Most of them point back to the galactic center, back to Sagittarius A star. It's the smoking gun. The black hole is flinging stars across the galaxy. There's also a population of stars that didn't escape but were perturbed into highly eccentric orbits. These stars spend most of their time far from the galactic center, but periodically plunge inward. When they do, they experience extreme conditions: high gravity, intense radiation, close encounters with other stars. It's a gauntlet. Some stars survive for many orbits. Others are disrupted on their first close pass. If a star gets too close, tidal forces tear it apart. The side facing the black hole is pulled more strongly than the far side. If the difference exceeds the star's internal gravity, the star is shredded. Gas streams out. Some falls into the black hole, some is flung away. The event produces a bright flare as the gas is heated and compressed. We've observed tidal disruption events in other galaxies, sudden bright flares from galactic cores, lasting weeks to months, then fading. Each one is a star being destroyed, consumed by a black hole. For Sagittarius A star, we haven't observed a tidal disruption event yet, but it's probably happened in the past and will happen in the future. The question is, when? Estimates vary, but it's probably a rare event, maybe once every 10,000 to 100,000 years. We might never see one during our lifetimes. But if we do, it will be a scientific bonanza. Every telescope will observe. We'll watch a star die in real time. We'll see the gas fall into the black hole. We'll measure the emission, the spectrum, the variability. We'll learn about the structure of the star, about the physics of tidal disruption, about accretion onto black holes. It will be a once-in-a-lifetime event. Maybe once in a civilization's lifetime. Now let's think about what would happen if you fell into Sagittarius A star. This is a thought experiment. You can't actually survive near a black hole. The radiation would kill you. The tidal forces would kill you. The lack of air would kill you. But let's imagine you're in an indestructible spacesuit with unlimited life support, and you decide to fall into the black hole. What would you experience? As you approach, the first thing you'd notice is the stars. They'd appear distorted. Light from stars behind the black hole would be bent around it. You'd see multiple images of the same star. Einstein rings, arcs of light. The black hole acts as a gravitational lens, bending and focusing light. The view would be surreal, trippy, unlike anything you've ever seen. As you get closer, you'd notice time dilation. Your watch ticks normally, but if you look back at a clock far from the black hole, it's ticking faster. Time is passing more quickly for them than for you. This effect increases as you approach the event horizon. If you hovered just above the horizon for a while and then returned, you'd find that centuries or millennia had passed in the outside universe. You'd have traveled forward in time, not by moving faster than light, but by exploiting the curvature of space-time. This is real. It's a consequence of general relativity. It's been measured with precise clocks on Earth and in orbit. Time runs slower in stronger gravitational fields. Eventually, you cross the event horizon. From your perspective, nothing dramatic happens. There's no barrier, no wall, no sign. You just cross an invisible boundary in space. But from this point, escape is impossible. All paths lead inward. If you fire your rockets trying to go back, you just delay the inevitable. You might slow your inward fall, but you can't stop it. You can't turn around. The event horizon is a one-way surface in space-time. Once crossed, Your future lies in the singularity. You can look back and see the outside universe. Light from outside can still reach you. You'd see the universe sped up, stars living and dying in fast forward, galaxies evolving. If you could survive long enough, you'd watch the entire future history of the universe play out. But you can't survive. You're falling inward. As you approach the singularity, tidal forces grow. Your feet are closer to the singularity than your head. They experience stronger gravity. The difference in force stretches you. At first, it's gentle, uncomfortable but survivable. But it increases without limit. Soon, it's unbearable. Your body is pulled like taffy. Bones crack, flesh tears. You're stretched into a long, thin stream of atoms. Spaghettification. It's a violent, horrible death. But it's also brief. Within fractions of a second, you're past the point of no return. The tidal forces rip you apart at the molecular level, then the atomic level. Electrons are stripped from nuclei. Everything is shredded down to elementary particles. And then those particles hit the singularity. What happens at the singularity is unknown. Our physics breaks down. The density becomes infinite. The curvature of space-time becomes infinite. General relativity gives nonsensical answers. Quantum mechanics might provide a description, but we don't have a quantum theory of gravity, so we don't know. You've fallen off the edge of known physics, into the realm of speculation and mystery. From the outside universe's perspective, you never crossed the event horizon. They saw you approach, slow down, freeze, redshift, fade. You're stuck at the horizon forever from their point of view. But from your perspective, you crossed smoothly and fell to your doom. Both are true. Relativity allows for different observers to have different but equally valid perspectives. There's no absolute time, no universal now, just different reference frames experiencing time differently. The role of Sagittarius A in the galaxy's history is profound. Supermassive black holes are thought to play a key role in galactic evolution. They regulate star formation. When a black hole feeds actively, it produces tremendous energy. This energy heats the surrounding gas. Hot gas expands. It becomes harder to compress into stars. Star formation slows or stops. This is called feedback. The black hole feeds, produces energy. The energy shuts off the fuel supply. The black hole starves, goes quiet. The gas cools. Star formation resumes. Gas accumulates near the black hole. It feeds again. The cycle repeats. This feedback mechanism might explain why galaxies have the masses they do, why the central black hole mass correlates with the galactic bulge mass. They're coupled. They co-evolve. Sagittarius A has probably gone through multiple feeding cycles over the galaxy's history. The Milky Way is about 13 billion years old. Sagittarius A might be almost as old. It probably formed early, perhaps from the direct collapse of a massive gas cloud, or from a cluster of stars collapsing together. Then it grew, accreting gas, merging with smaller black holes. Each feeding episode added mass. Each merger added mass and spin. Over billions of years, it grew from perhaps a few 100,000 solar masses to its current 4 million. And it shaped the galaxy in the process. The feedback from its active phases regulated star formation. The gravitational influence organized stellar orbits. Without Sagittarius A star, the Milky Way would be a different galaxy, smaller, less organized, maybe without a defined structure. The black hole is not just a resident of the galaxy, it's an architect. Future observations will reveal more about Sagittarius A star. New telescopes are being built. New techniques are being developed. The Event Horizon Telescope continues to improve, adding more dishes and increasing resolution. Future observations might capture variability in the ring structure. We might see material spiraling into the black hole in real time. We might observe the effects of the black hole's spin on the accretion disk in detail. There's also the possibility of detecting gravitational waves from Sagittarius A star, not from the black hole itself sitting there quietly, but from objects falling into it. If a stellar mass black hole or neutron star spirals into Sagittarius A star, it produces gravitational waves. These waves would be detectable by future space-based gravitational wave observatories like LISA, the Laser Interferometer Space Antenna. LISA is planned to launch in the 2030s. It will be sensitive to lower frequency gravitational waves than LIGO, the kind produced by supermassive black hole mergers or by objects falling into them. If we're lucky, LISA might detect events from Sagittarius A star. Each detection would tell us about the population of compact objects near the galactic center. There are also plans for infrared observatories that could study the stars near Sagittarius A star in even greater detail, tracking their orbits with higher precision, detecting smaller accelerations and perturbations, looking for planets around these stars, which seems unlikely, but you never know, testing general relativity in even more extreme regimes. Each new observation adds pieces to the puzzle. We've come incredibly far in a few decades, from not knowing Sagittarius A star existed to imaging its shadow, but there's still so much to learn. Every answer raises new questions. Why is the accretion rate so low? What determines when the black hole becomes active? How exactly do supermassive black holes form? What happens at the singularity? Can we develop a theory of quantum gravity? The questions are endless. And that's what makes this exciting. We're not done. We're just getting started. The philosophical implications of Sagittarius A star are worth considering too. We live in a galaxy with a supermassive black hole at its center, a monster, a destroyer, an object so extreme that it defies intuition, and yet we're safe. We're far enough away that we can study it without being threatened by it. We can observe, learn, marvel. This is a privilege. We live in an era with the technology to detect and study black holes. Our ancestors couldn't. They looked at the same sky but saw only stars. They didn't know about the beast at the center. Future generations will know more than we do. They'll have better telescopes, better theories, but they'll build on what we've learned. We're part of a continuum, a chain of discovery stretching back to the first humans who looked up and wondered, stretching forward to future scientists who will solve mysteries we can barely articulate, And there's something humbling about knowing that we orbit a black hole, that our entire solar system, our planet, our civilization, is held in the gravitational grip of something we can't see. We feel the sun's gravity. We feel Earth's gravity. But Sagittarius A star, it's too far away. Its influence is too subtle. We don't feel it directly, but it's there, pulling on us, shaping our orbit around the galaxy. We're part of a vast cosmic dance. The sun orbits the galactic center every 230 million years. This is called a galactic year. The last time the sun was in its current position, dinosaurs were just beginning to evolve on Earth. The next time it completes an orbit, dinosaurs will be long gone. Mammals will have risen and perhaps fallen. Maybe a new form of life will dominate Earth, or maybe Earth will be uninhabitable. The sun will have swelled into a red giant. The oceans will have boiled away, but the galaxy will continue. A star will continue, indifferent to our fate. This perspective is both terrifying and comforting. Terrifying because it shows how small we are, how temporary, one planet among billions, one species among billions that have lived and died. One moment in cosmic history. But it's also comforting because it means our problems, our conflicts, our anxieties, they're temporary too. They're local. They matter to us, but not to the universe. The universe doesn't care if we succeed or fail. It will go on regardless. This can be liberating. It frees us to focus on what matters, to make the most of our brief time, to cherish the moments we have, to be kind to each other, to seek understanding, to create beauty, to love, because in the grand scheme, that's all we have. Our connections, our experiences, our curiosity, our wonder. Sagittarius A star reminds us that the universe is stranger and more magnificent than we can imagine. Black holes, space-time, relativity, quantum mechanics. These ideas are bizarre. They violate common sense. They challenge our intuitions. But they're real. They're how the universe works. And we've figured them out. Not completely, not perfectly, but we've made incredible progress. From Newton's laws to Einstein's relativity, to quantum field theory to the Event Horizon Telescope. We've built on generations of thought and observation. We've developed mathematics and technology. We've asked questions and sought answers. And we'll keep going, keep pushing the boundaries, keep exploring, because that's what we do. That's what makes us human. Curiosity, the desire to understand, to know, to see. Even if what we're seeing is a black hole, even if it's invisible, even if it challenges everything we thought we knew, we look, we measure, we think, and slowly, piece by piece, we understand. Let's explore the concept of the photon sphere in more detail because it's one of the most bizarre features near a black hole. The photon sphere is a region where gravity is so strong that light can orbit the black hole. Imagine a photon, a particle of light, traveling tangentially around the black hole. At just the right distance, about 1.5 times the event horizon radius, the curvature of space-time is such that the photon's path curves into a circle. The photon orbits the black hole forever. Well, not quite forever, because the orbit is unstable. The slightest perturbation sends the photon either falling inward to the event horizon or escaping outward to infinity. But mathematically, the circular orbit exists. This is the photon sphere. If you were somehow at the photon sphere and looked sideways, tangent to your orbit, you could theoretically see the back of your own head. Light from the back of your head would travel around the black hole and arrive at your eyes. You'd see yourself from behind. If you had a really good telescope, you'd see infinite images of yourself, each one circling the black hole another time before reaching you. It's trippy, mind-bending, and it follows directly from the mathematics of general relativity. Einstein's equations predict this. They predict that light near a black hole doesn't travel in straight lines. It curves, circles, spirals. The universe near a black hole is a hall of mirrors, geometry twisted into impossible shapes. The photon sphere is why the shadow in the event horizon telescope image is larger than the event horizon itself. The shadow is about 2.5 times the radius of the event horizon. Light that passes inside the photon sphere gets captured. It spirals inward and crosses the event horizon. So from far away, you can't see anything inside the photon sphere. It appears dark, a shadow. The bright ring in the image comes from light that's just outside the photon sphere. Light emitted by the accretion disk. Some of that light escapes to reach us, but it's been bent and amplified by the black hole's gravity. The image is distorted, magnified, brightened, reality warped by extreme gravity. There's also the question of what exists inside the event horizon. We can't observe it. No information escapes, but we can theorize. General relativity tells us that inside the horizon, all paths lead to the singularity. You can't orbit. You can't hover. You can only fall. The singularity is in your future no matter what you do. But how long does it take to reach it? That depends on the size of the black hole. For stellar mass black holes, the journey from horizon to singularity is brief. Fractions of a second. Tidal forces become infinite. You're destroyed almost immediately, but for supermassive black holes like Sagittarius A star, the journey is longer, maybe tens of seconds or even minutes. The event horizon is so large that tidal forces at the horizon are relatively gentle. You could cross and survive for a while. You'd have time to look around, to observe. Of course, there's nothing to see. You're inside a black hole. The only light is what you brought with you or what came in with you. And that light is doomed too. It's falling toward the singularity just like you. One speculation is that the interior of a black hole might connect to other regions of space-time, wormholes, bridges to other universes or other points in our universe. This comes from solutions to Einstein's equations. The Schwarzschild solution, which describes a non-rotating black hole, mathematically includes a white hole on the other side. A white hole is the time reverse of a black hole. Instead of absorbing everything, it expels everything. Nothing can enter a white hole. Everything is pushed away. The Schwarzschild solution connects a black hole to a white hole through a wormhole, an Einstein-Rosen bridge. But this is mathematical. Does it exist in reality? Probably not. the wormhole would be unstable. It would pinch off before anything could travel through, and we've never observed a white hole. They might not exist, or they might be so rare or so brief that we've never detected one. For rotating black holes described by the Kerr solution, the mathematics is even more exotic. There are inner event horizons, ring singularities instead of point singularities, closed time-like curves where you could theoretically travel backward in time. But again, these are mathematical solutions. They assume idealized conditions that don't exist in the real universe. Real black holes have irregularities. They accrete matter. They merge with other black holes. All of this disrupts the perfect symmetry required for these exotic structures. Most physicists think wormholes and time travel are mathematical curiosities, not features of physical black holes. But we don't know for sure. The interior of a black hole is hidden from us. We can theorize, but we can't observe, not without crossing the event horizon ourselves. And no one's volunteering for that trip. Now, let's talk about the mass of Sagittarius A star more carefully. We've said it's 4 million solar masses. But how precisely do we know this? The mass is inferred from the orbits of stars around it. Newton's laws and Kepler's laws tell us that the orbital period and the size of the orbit are related to the mass being orbited. By measuring the period and the orbit size, for stars like S2, we can calculate the mass, and the answer is about 4.15 million solar masses. There's some uncertainty, maybe plus or minus a few 100,000 solar masses, but we know it's in that range. The precision has improved over decades of observation. As we track more orbits and get better measurements, the uncertainty shrinks. We're confident in the 4 million figure. But there's an interesting question. Is all that mass in the black hole? Or could some of it be in stars or gas or dark matter distributed around the black hole? To answer this, we look at how the mass is concentrated. If the mass were spread out, the gravitational effects would be different. Stars orbiting at different distances would reveal a distributed mass. But observations show that the mass is concentrated at a single point, within a region smaller than the orbit of Mercury. The only object we know of that can pack 4 million solar masses into such a small volume is a black hole. Nothing else is that dense. So we're confident that Sagittarius A star is a supermassive black hole, not a cluster of dark matter, not a cluster of neutron stars or stellar mass black holes. A single supermassive black hole. Let's also consider the question of whether Sagittarius A star could have a companion. Could there be another black hole orbiting it? This isn't as crazy as it sounds. Binary black holes exist. We've detected them with gravitational wave observatories. Stellar mass black holes orbiting each other, spiraling inward, merging. Could Sagittarius A star have a companion? If it did, the companion would perturb the orbits of nearby stars in detectable ways. We'd see periodic variations in stellar positions, deviations from simple Keplerian orbits. But we don't see this. All the stars orbit as if there's a single central mass. So, if there's a companion, it's much less massive than Sagittarius A star. Small enough that its gravitational influence is negligible. Maybe a few thousand solar masses or less. We can't rule out a small companion, but there's no evidence for one. In the future, if another supermassive black hole approaches Sagittarius A star, perhaps from a dwarf galaxy being consumed by the Milky Way, the two black holes would interact. Initially, they'd orbit each other at large distances. Over time, gravitational interactions with stars and gas would sap their orbital energy. The orbit would shrink. This process is called dynamical friction. The black holes would spiral closer. Eventually, they'd get close enough that gravitational wave emission becomes important. Gravitational waves carry away energy. The orbit shrinks faster and faster. In the final moments, the black holes are orbiting hundreds of times per second, emitting tremendous gravitational waves, and then they merge. The event horizons touch, combine. A single larger event horizon forms. The merged black hole settles down into a stable state. It might be spinning rapidly. It might be emitting a last burst of gravitational waves as it wobbles and stabilizes. This merger is one of the most energetic events in the universe. More energy released in gravitational waves than the sun will emit in light over its entire lifetime, and it's completely silent. No light, no sound, just ripples in space-time spreading at the speed of light. The prospect of Sagittarius A star merging with another black hole is not immediate. It would require a companion to approach. The Milky Way does consume smaller galaxies. We're currently in the process of absorbing a few dwarf galaxies. The Sagittarius dwarf elliptical galaxy, for instance, is being torn apart by the Milky Way's gravity. Its stars are being assimilated. If it had a central black hole, and it probably did since most galaxies do, that black hole is now somewhere in the Milky Way. It might eventually sink to the center and merge with Sagittarius A star. But that process takes a long time, billions of years. The black hole has to lose orbital energy. It does this through dynamical friction, interacting gravitationally with stars. Each interaction transfers a tiny amount of energy. Slowly, over eons, the orbit decays. The black hole spirals inward, eventually reaching the galactic center. Then it merges with Sagittarius A star. This has probably happened multiple times over the Milky Way's history. Sagittarius A star has likely grown by merging with smaller black holes from consumed galaxies. Each merger added mass and spin. Let's think about what Sagittarius A star was like in the early universe. 13 billion years ago, shortly after the Big Bang, galaxies were just forming. The Milky Way was a collection of smaller proto-galaxies. Gas clouds collapsing under gravity, stars forming, and at the centers of these proto-galaxies, the first black holes were forming. We don't know exactly how, but by the time the proto-galaxies merged to form the Milky Way, Sagittarius A star was already there. Probably smaller, maybe a few 100,000 solar masses. It grew as the galaxy grew, accreting gas during periods of active star formation, merging with black holes from infalling satellites, becoming more massive over time. In the early days, Sagittarius A star was probably more active, more gas available, higher accretion rates. It might have been a quasar, blazingly bright, outshining the entire galaxy, jets streaming outward, Feedback heating the gas, regulating star formation, shaping the galaxy's evolution. Over billions of years, the activity declined. The gas was consumed or heated or blown away. Sagittarius A star settled into its current quiet state, dormant, waiting. If new fuel arrives, it will wake up, but for now, it sleeps. The discovery of Sagittarius A star and its detailed study over the past few decades represents one of the great achievements of modern astronomy. We've gone from suspecting there might be something unusual at the galactic center to proving there's a black hole there to imaging its shadow. Each step required new technology, better telescopes, more sensitive detectors, clever analysis techniques, and collaboration. Scientists from around the world working together, sharing data, building on each other's work. This is how science progresses, not through lone geniuses, but through collective effort. Generations of researchers, each adding a piece, each answering a question and raising new ones. And the story isn't over. We're still learning, still observing, still theorizing. Each new observation of Sagittarius A star reveals something unexpected. Each theoretical advance opens new questions. We're in the early stages of understanding supermassive black holes. We know they exist. We know roughly how they behave, but the details are murky. Why do some galaxies have active black holes while others are quiet? How do black holes regulate star formation? What determines the spin of a supermassive black hole? How do they merge? What happens to the gas around them? These questions don't have complete answers. We're working on them, and every new piece of data helps. There's something deeply satisfying about studying objects like Sagittarius A star. They're extreme, alien, unimaginable, and yet we can understand them, we can measure them, we can predict their behavior, we can test our theories against observation. This is the power of science. It allows us to transcend our limitations. We're hairless apes on a small planet, limited lifespans, limited senses. We can't see X-rays or radio waves. We can't survive in space. We're fragile, weak, but we're also clever. We build tools. We develop mathematics. We collaborate. We think. And through these efforts, we can comprehend a black hole 4 million times more massive than the Sun, 26,000 light years away. We can image it. We can understand how it formed, how it evolved, what it does. This is extraordinary. This is what makes us human, not our physical strength, not our senses, our minds, our curiosity, our drive to know. The connection between Sagittarius A star and dark matter is worth exploring. Dark matter is the mysterious substance that makes up about 85% of the matter in the universe. We can't see it. It doesn't emit light. It doesn't absorb light. It doesn't interact with electromagnetic radiation at all, as far as we can tell. But it has mass. It produces gravity. We know it exists because we see its gravitational effects. Galaxies rotate faster than they should based on the visible matter. Clusters of galaxies hold together despite not having enough visible mass. Gravitational lensing shows that there's more mass than we can see. All of this points to dark matter, invisible matter that only interacts through gravity. The galactic center is thought to have a high concentration of dark matter. Models predict that dark matter should accumulate near the black hole. It's pulled in by gravity. It orbits Sagittarius A star just like the stars do, but we can't see it. Does this matter? It might. The dark matter contributes to the total gravitational field. If there's a lot of dark matter near Sagittarius A star, the measured mass from stellar orbits would include both the black hole and the dark matter. We'd be overestimating the black hole's mass, but calculations suggest this effect is small, maybe a few percent at most. The vast majority of the central mass is the black hole itself, not dark matter. Still, there might be dark matter there, and if there is, it could interact with the black hole in interesting ways. Dark matter particles falling into the black hole, annihilating near the event horizon, producing radiation. This is speculative. We haven't detected such signals, but it's a possibility, something to look for in future observations. Another aspect to consider is the role of magnetic fields in the environment around Sagittarius A star. Magnetic fields are generated by the motion of charged particles, plasma in the accretion disk, stellar winds from nearby stars. This plasma is threaded with magnetic field lines. These fields can store enormous amounts of energy. They can also transport angular momentum. When matter spirals into a black hole, it has to lose angular momentum. Otherwise, it would just orbit forever. One way to lose angular momentum is through friction. Matter in the disk rubs against other matter, transfers momentum. Another way is through magnetic fields. Magnetic forces can extract angular momentum from the inner disk and deposit it farther out. This allows the inner material to fall inward while the outer material moves outward. It's called magnetohydrodynamic turbulence, and it's essential for accretion. Without it, black holes couldn't grow. Material would pile up in stable orbits and never fall in. The magnetic fields near Sagittarius A star are also responsible for some of the variability we observe. The fields can become tangled and twisted. They can reconnect, releasing energy in bursts. This might explain the X-ray and infrared flares that Sagittarius A star occasionally produces. These flares are unpredictable. They last for a few hours. They're much brighter than the baseline emission. During a flare, Sagittarius A star might brighten by a factor of 10 or more in X-rays. Then it fades back to normal. We're not entirely sure what causes the flares. Magnetic reconnection is one theory. Hotspots in the accretion disk is another. Maybe both processes contribute. Each flare is an opportunity to study the dynamics near the event horizon. To understand how matter behaves in extreme conditions, let's also discuss the future evolution of Sagittarius A star. Over the next billions of years, what will happen to it? In the short term, not much. Sagittarius A star is in a quiescent state. It will remain that way until something provides new fuel. In about 4 billion years, the Milky Way will collide with Andromeda. This will funnel gas toward both galactic centers. Sagittarius A star will wake up. It will feed. It will become active, possibly a quasar. This active phase might last a few million years. Then the fuel runs out. SGR A star goes back to sleep, but it's more massive now. The merger with Andromeda's black hole added mass. SGR A star might be 5 or 6 million solar masses after the merger, maybe more. Over even longer timescales, tens or hundreds of billions of years, star formation in the merged galaxy will slow and eventually stop. All the available gas will be used up or dispersed. No new stars will form. Existing stars will age and die. The galaxy will become a collection of white dwarfs, neutron stars, and black holes. Dead stellar remnants orbiting in the dark. And at the center, SGR A star will remain. Now, perhaps the dominant source of gravity in the galaxy. Almost all the mass in stars will have been converted to compact objects. Some of those compact objects will fall into Sagittarius A star. Over trillions of years, the black hole will continue growing, slowly, accreting the occasional stellar remnant or stellar mass black hole that wanders too close. Eventually, perhaps after about 100 trillion years, the galaxy will be a dark, cold place. No stars, no light, just dead remnants and Sagittarius A star. And the black hole will start to evaporate. Hawking radiation emitted from near the event horizon due to quantum effects slowly carries away energy. The black hole loses mass. For SGR A star, the evaporation time is about 10 to the 100 years. That's a 1 with 100 zeros after it. An incomprehensibly long time. The current age of the universe is about 14 billion years. 10 to the 10 years. SGR A star will outlast the stars by a factor of 10 to the 90. It will sit in the cold, dark universe for eons, slowly radiating, slowly shrinking, until finally, after an eternity, it evaporates completely. The last bit of mass converts to radiation, a final flash, and then nothing. The black hole is gone. Only photons remain, spreading through the ever-expanding void. This is the ultimate fate of everything. Heat death, maximum entropy. The universe cold, dark, and empty. No stars, no galaxies, no black holes, no structure. Just diffuse radiation cooling toward absolute zero as space expands. It's a bleak picture, but it's also distant, unimaginably distant. For now, the universe is young, full of stars and galaxies and black holes, full of structure and complexity. We live in a special time, a time when the universe is interesting, when there are things to observe and study and wonder at. This won't last forever, but it will last for trillions of years. Plenty of time for civilizations to rise and fall, for intelligence to explore and understand, for consciousness to contemplate existence. And that brings us to the question of other civilizations. Are there other intelligent beings in the galaxy? Other species looking at Sagittarius A star and wondering what it is? We don't know. We haven't detected any signals. No radio transmissions, no laser pulses, no obvious signs of technology. Either we're alone or other civilizations are rare, or they're quiet, or we're not looking in the right way. The Fermi paradox. If intelligent life is common, where is everyone? Why don't we see them? The galaxy is billions of years old. There's been plenty of time for civilizations to arise and spread. Maybe they're out there but too far away. Maybe they don't want to communicate. Maybe they went extinct. Maybe intelligence is a brief phase. Species develop technology, destroy themselves, and vanish. Maybe we're the first, or maybe we're just not looking carefully enough. If there are other civilizations, they might be studying Sagittarius A star too. From their vantage points in the galaxy, they'd see it from different angles, different perspectives. We see it from 26,000 light-years away in one direction. A civilization on the opposite side of the galaxy would see it from 26,000 light-years in the opposite direction. Same black hole, different view. If we could somehow communicate with them, we could combine our observations, get a three-dimensional picture of the galactic center, understand it from multiple angles. But that's science fiction. For now, we're alone in our observations, building our understanding with our own tools and our own ingenuity. The study of Sagittarius star also connects to broader questions about the nature of reality. What is space-time? Why does it curve? What is gravity really? Einstein gave us a mathematical framework. General relativity. It describes how mass and energy curve space-time and how that curvature manifests as gravity. The equations work. They make predictions that match observations, but they don't explain why. Why does mass curve space-time? Why does curvature produce what we experience as gravity? These are deep questions. Questions that might not have answers in the way we'd like. Physics describes how things work, not why. The why might be unanswerable, or it might require a deeper theory, a theory we haven't discovered yet. Quantum gravity is the holy grail, a theory that unifies general relativity and quantum mechanics. That explains gravity in quantum terms. That resolves the contradictions between the two frameworks. String theory is one candidate. Loop quantum gravity is another. There are others, but none have been confirmed. None make testable predictions that we can verify with current technology. We need observations of regimes where both quantum mechanics and strong gravity are important. The interior of black holes, the Big Bang, the singularity at the center of Sagittarius A star. These are the places where quantum gravity matters, but we can't observe them directly, so we're stuck theorizing, building mathematical models, hoping that someday we'll find a way to test them. Black holes like Sagittarius A star are key to this quest. They're laboratories for extreme physics, conditions we can't recreate on Earth, conditions that push our theories to their limits. Every observation of Sagittarius A star is a data point, a constraint on theories. Test of our understanding. If our theories predict one thing and observations show another, we learn something. We refine the theories, or we discard them and develop new ones. This is how science works. Predict, observe, compare, refine, repeat. Slowly, over decades and centuries, we build a more accurate picture of reality. Sagittarius A star is also a reminder of the limits of human perception. We can't see the black hole directly. We can't visit it. We can't experiment with it in a controlled way. We're limited to passive observation, watching from afar, using light and other signals that have traveled 26,000 years to reach us. And yet, from these limited observations, we've learned so much. We've measured the black hole's mass, mapped its environment, imaged its shadow, tested general relativity. These achievements are remarkable given our constraints. It shows what's possible when you're clever, when you develop the right tools and techniques, when you think carefully about what you can and can't measure and how to extract information from noisy data. It also shows the value of patience. The observations of SGR A star span decades. Researchers started watching the galactic center in the 1990s. Some of them are still watching today. That's careers spent on one project. One question: is there a black hole at the center of the galaxy? What are its properties? This long-term commitment is rare in modern science, where funding and careers depend on quick results. But it's necessary for some questions. You can't rush a star's orbit. You have to wait, watch, record, year after year, building up the data, until finally you have enough to draw conclusions. The Nobel Prize, awarded in 2020, recognized this patience, this dedication, this long view. And the work continues. New graduate students join the effort. New telescopes come online. New techniques are developed. The next generation builds on what came before. This is the nature of scientific progress. It's cumulative. Each generation stands on the shoulders of giants, sees a little farther, understands a little more, and leaves a foundation for the next generation to build on. SGA star will be studied for as long as humans exist. It's a natural wonder, a cosmic monument, a reminder of the strange and beautiful universe we inhabit. Thank you for exploring Sagittarius A star with me. If this journey into the heart of our galaxy expanded your sense of the cosmos, a like or subscribe really helps the channel keep investigating these profound mysteries. And remember, you're not just on Earth. You're on a planet orbiting a star that's orbiting a supermassive black hole. We're all falling around a monster, but instead of fear, we can feel wonder. Instead of helplessness, we can feel empowered by knowledge. We understand what's happening. We can measure it, study it, marvel at it. That's the gift of science. It turns cosmic terror into cosmic beauty. The black hole at the center of our galaxy is not our enemy. It's our anchor, our center, the heart around which everything turns. Good night, and may you never forget the invisible monster that holds the stars together.